Hey everyone, in this mini lecture we're going to look at the topic of linear programming. We'll call it LP for short. So what is linear programming? Basically what it is just this model that we're creating that consists of linear relationships representing some objective and also some resource constraints. So LP, or linear programming, is this mathematical modeling technique that's used to determine um, a level of operational activity, right? Mostly for companies or firms or whatever have you. And this is in order to achieve an objective for them, right? And that objective is subject to different restrictions, which we call constraints. So linear programming is applied to many different fields of mathematics and engineering, um, applied business um, areas, and so forth. Different types of problems, from transportation problems, product mix problems, assignment problems, budgeting, shortest route problems, trim lost, facility locations, and so forth. So what LP model formulation consists of are first decision variables. So decision variables are the mathematical symbols representing levels of activity of an operation. Next, there are what's called an objective function. So that's a linear relationship reflecting the objective of the overall problem. So most frequent objectives let's use a business for an example. The most frequent objective of a business firm is to maximize profit, right? Maybe individual operation units like a packaging department, they want to minimize the cost. So those are objective functions. And then there's the constraint. So that's a linear relationship that's representing a restriction on decision making. Okay, let's take a look at our LP model formulation. So we have the top line. You see the maximum minimum, right? This is known as the objective function right there. You see the maximum minimum, and we're going to choose one of these depending on what the problem is asking for. If it's a maximization problem, we'll write max, z is equal to, so forth. And then we have all of these here. This shows you the equations for the constraints, right? A sub 11 times x sub 1 plus a sub 12 times x sub 2, and so forth. And depending on the problem, it could be an inequality, right? Less than or equal to, greater than or equal to, or it could just be an equal to for the equation. And that will be equal to the b sub 1, whatever value is given in the problem. And then we may have more than one constraint. We have maybe 2 or even 3 or even more than that, depending on your problem. And then here's what all of the variables stand for, right? X sub j will be the decision variables, B sub I is the constraint levels, C sub j objective function coefficients, and A sub ij are the constraint coefficients. All right, let's take a look at an example really quickly. So let's say we have this example where we have this company, um, they're using clay to produce products of either a bowl or a mug. And this is the given information, right? So we're given this information here. So they give it to us usually in the form of a word problem, but in this example, they're giving it to us in a tabular form. All right, so the products are bowl and mug. So the bowl, the labor is 1 hour for every unit, and then there's 4 pounds of clay for every unit for the bowl, and the revenue is $40 per unit. And then we have for the mug, that production, the labor is 2 hours for every unit to be produced, for every unit of a mug. The clay is 3 pounds used for every unit, which is the mug. And the revenue is $50 for every mug. All right, then they're telling us that there are 40 hours of labor and 120 pounds of clay available each day. So the decision variables we always have to come up with on our own, and they are x sub 1 and x sub 2. X sub 1 is the number of bowls to produce, and x sub 2 is the number of mugs to produce. And just understand that we're using x sub 1 and x sub 2. That's the convention usually in LP models, but sometimes in other texts they may just use x for x sub 1 and maybe even just y for x sub 2. So the decision variables are the number of bowls to produce and the number of mugs to produce. So let's dig into it and create our model. So if we're talking about a company and we're looking at the number of bowls to produce and the number of mugs to produce, we're trying to most likely maximize our revenue, right? So this will be a maximization problem. We would write that down. And then we would say, okay, let's say Z is equal to $40. Just looking at our problem, we're trying to maximize the revenue, right? So $40, and it says per unit. Well, x sub 1 is the number of bowls, so $40 times x sub 1 plus $50 times x sub 2. So you have to come up with this objective function, which we just did. We looked at the problem and we determined that they're trying to, if they don't explicitly tell us, then we have to figure out what they're probably trying to do. For a company like this, given this amount of information, look like they're probably going to want to maximize the revenue. So it's MAX instead of MIN versus minimization. Z is equal to, we always use Z equals something to create that answer of the maximum revenue. And then what they gave us, the 40 times the x sub 1, 50 times x sub 2. Right, and then we can write subject to, sometimes they just write s dot t as it is abbreviated, but I'll write it out, subject to, and these will be the constraints. Remember we talked about the constraints? So it looks like you have to go back in the problem and take a look and say, what are the constraints? Well, we said these are the constraints, right? Constraints are things that you have to adhere to or that'll restrict certain things within the problem. And here are the restrictions. There are only 40 hours of labor and 120 pounds of clay available each day. So 40 hours of labor. So 40 hours of labor. So we have to write it's subject to x sub 1, the bowls, and it's 1 times that, right? But we don't have to write a 1. Well, I will. 1 times x sub 1 plus 2 times x sub 2 has to be less than or equal to 40 hours. Please take a look at where I got the 1 and the 2 from. I got them right up there because we're talking about this one. I'm sorry. We're talking about this one out here. There are 40 hours of labor, right? So labor is for the bowl and the mug. What's the other constraint? 120 pounds of clay each day. This is the labor constraint. The next one I'm going to write is the clay constraint. So please take a look at where the numbers are coming from. 4 times x sub 1 plus 3 times x sub 2. Where does that come from? Well, right here in that second column. Right? And that has to be less than or equal to what? Well, it says it up here, 120 pounds per day. 120 pounds. All right, so a problem like this, we could just take the constraints and solve it as a system of equations, especially the one right here because it has 2 equations and 2 unknowns. We're used to doing that, right? Substitution method, elimination method, and so forth. However, sometimes there are more and more and more equations, so we'll have to use some type of software. But in this case, I want to look at it graphically. I'm going to try to look at this graphically. So I'm going to use a graphing tool such as Desmos. All right, so I have Desmos pulled up. Just went to desmos.com, and usually it gives you the entire Cartesian coordinate system, but I went to the far right, the wrench graph settings, and I changed mine up a little bit. So if you want to change your x-axis, I changed mine so it'll just basically the x and y axis. I wanted to just show me that first quadrant of our xy coordinate system. So my x-axis is from 0 to 60 and my y-axis is from 0 to 50. Usually it'll go from negative to positive on both, but I changed mine up ahead of time. So now I'm just going to go ahead and plug in our restraints, right? I'm going to use x and y with Desmos instead of x sub 1 and x sub 2. So I'm going to write x plus 2y, and then it's less than, I think our problem said less than or equal to 40, right? So it looks like that. And then the next constraint, so this was the labor constraint. These are the 2 things that you'll graph. The next one was 4x plus, and again, instead of using x sub 1 and x sub 2, I'm using x and y. X sub 2 will be my y. So 4x plus 3y. And we said this had to be less than or equal to. So if you type the less than symbol and then type the equal to symbol, it'll change it to the inequality less than equal to for you. And we said this had to be 120. Right? So let's take a look at this. So this purple region, this is known as my feasible region, right? So I'm gonna look at all the vertices, but still I'm just gonna keep looking at that first quadrant. So within my feasible region, I'm gonna look at the outer areas because it's a maximization problem, and look at all of the vertices. So the vertices will be right here, right? Whatever value that is, we have to let Desmos tell us. So there it is. So Desmos is telling us that is 0, 20. So make note of that if you're taking notes, 0, 20. And then, so 0 is the x, 20 is the y. The next vertex, and it has it there for me, is 24, 8. X is 24, y is 8. And then the next one right here is 30, 0. X is 30, y is 0. So make sure we've written those down. 0, 20, 24, 8, and 30, 0. Alright, so what I'm going to do now is take those values 0, 20. So 0 is going to be my x sub 1, 20 will be my x sub 2. So I'm going to take those and plug them into my objective function. 40x sub 1 plus 50x sub 2. So if I plug in x sub 1, x sub 1 is 0, and then x sub 2 is my y value, so that's 20. So I'm going to get 0 plus 1,000, right? So I get 1,000. $1,000 is the revenue at that point. Alright, so now I'm going to do the next one, which is the 24, 8. Alright, so 0 equals 40x sub 1, plugging that into my objective function 2, so 24, 8. 24 is my x sub 1, so 40 times 24 plus 50 times 8. Right, and then just break out your trusty calculator. So 40 times 24 gets me about 960. 50 times 8 is 400. So 400 plus 960. Alright, that gets 1,360. Alright, and then we said we're going to use that other one. So look at all the vertices. Those are the 3 vertices. Alright, that one is the 30, 0. Okay, so I'm not going to write the actual objective function over. I'm just going to start plugging in 40 times 30 plus 50, times 0. Right, so that makes 0, 0, 1,200, right? Because 50 times 0 is 0. So the revenue there is $1,200. So it looks like the optimum for maximization is that one right there, where we have x1 is 24. What was x1? X1 was bowls. X1 was bowls, so 24 bowls. And x2 should be, for maximization, what was the x2 value? 8 for that point right there. So 8. And then that should be the mugs. So that's where they get the maximum revenue. 24 bowls sold and 8 mugs sold. The maximum revenue comes out to be $1,360.